our last lecture we had considered a Hermitian matrix H naught which had twofold degeneracy. We applied a perturbation, we framed the secular determinant and found out the first order perturbation to the eigenvalues. The matrix that we had started out with H naught was equal to 1 0 0 1, which has eigenvalue plus 1, and it is a twofold degeneracy. And then we said that let this perturbation be very simple perturbation epsilon 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 epsilon, and we chose the base states as ket 1 is equal to 1 0 and ket 2 is equal to 0 1. So, my all the matrix element H prime 1 1, H prime 1 2, H prime 2 1, H prime 2 2, they are all equal to epsilon. So, we set up the secular equation and we found that C 1 H prime 1 1, the equation is H prime 1 1 minus W 1 plus C 2 H prime 1 2 is equal to 0, and then C 1 H prime 2 1 plus C 2 H prime 2 2. If you understand this part clearly, then everything will become clearer. So, all these matrix elements are epsilon, and we found that the values of W 1 was either 0 or 2 epsilon. So, let me consider 0 first. So, W 1 is 0. So, we have C 1 epsilon plus C 2 epsilon is 0. So, C 1 plus C 2 is equal to 0. Even this equation will give me the same thing. W 1 is 0, this is 1, this is epsilon, C 1 plus C 2 is equal to 0. So, therefore, C 2 is equal to minus C 1. So, my eigenstate that corresponding to the eigenvalue splits, and the eigen function is 1 minus 1 divided by under root of 2. Under root of 2 is just to normalize it. You can put minus 1 and 1 also, that is also all right. Now, we take then 2 epsilon, W 1 is equal to 2 epsilon. So, we have if W 1 is equal to 2 epsilon, so H prime 1 1 is epsilon, epsilon minus 2 epsilon is minus epsilon. So, minus epsilon C 1 1 plus C 2 epsilon, this is equal to 0. So, epsilon epsilon cancels out, sorry, C 1. So, C 1 becomes equal to C 2. So, my eigenket becomes, so it is C 1 U 1 plus C 2 U 2. So, this was C 1 is equal to C 2. So, my eigenket becomes 1 1 under root. So, therefore, you have the degenerate state had only one eigenvalue 1 plus 1. When you apply the perturbation, it splits into two states. One, the perturbation is 0, and the second is 2 epsilon. So, the splitting is 2 epsilon. This wave function is say ket 3 is equal to 1 minus 1 divided by root 2, and this wave function say ket 4, this is equal to 1 over root 2 1 1. So, this is a twofold degenerate state, it splits into two states. Let me find out the exact. The the one more thing that I want to mention, that we could have equally well started with these eigenkets. Let us suppose instead of 1 0 and 0 1, we had started with this case, that is, we had assumed that 1 was equal to under root of 2 1 1 and 2 is equal to 1 over root 2 1 minus 1. Now, notice that what is h prime 1 1? H prime 1 1 is equal to, so this is 1 h prime 1. So, this is equal to half 1, the bra 1 will be 1 1 epsilon 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 1 1. So, this will be epsilon plus epsilon, 2 epsilon here and 2 epsilon here. So, you simple analysis will show that this will be equal to 2 epsilon. It will come out to be 4 epsilon. Then let me calculate the other eigenvalues, the other matrix elements. H prime 1 2, H prime 1 2 will be bra 1 H prime 2, and therefore, this will be 1 by 2 1 1 epsilon 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 and 1 minus 1. Now, please see epsilon minus epsilon, that is 0, and epsilon minus epsilon, that is 0. So, this becomes 0. In fact, all other matrix elements are 0. So, that H prime 1 2 is equal to H prime 2 1 is equal to 0, and H prime 2 2 also happens to be 0. So, if you write down the H prime matrix, then it will be 2 epsilon 0 0 0. It is a diagonal matrix and the eigenvalues are 2 epsilon and 0, and the off diagonal elements are 0. So, we now have a representation in which we have chosen our base states such that H prime is a diagonal matrix, and so therefore, if we choose initially those wave functions for which H prime is a diagonal matrix, then the diagonal elements will be the eigenvalues, will be the perturbation. And this also follows from, if you recollect, that we had started with this, and then we said that we multiplied by, we wrote down psi n 1 as E m 1 E m, then we multiplied by u k star and had obtained this equation. Now, if you just look at this equation, then first we had considered k is equal to n, but let me consider the case when k is not equal to n, but E k is equal to E n. That is, I am considering multiplication between those states for which the energies are equal, but the wave functions are different. So, E k is equal to E n. So, this term gets cancels with this term, and then it will become W n 1 So, therefore, k is not equal to n. So, this term is 0. So, my H prime k n must necessarily be 0. That means, and then if I have chosen that representation in which my H prime k n, H prime matrix is diagonal, then the diagonal elements will represent the perturbation to this state. We will illustrate this again if you have not followed through another example. Now, before I continue further, let me also mention that the total matrix H is given by epsilon, this is H naught plus H. So, H prime was equal to H this thing and H naught was equal to 1 0 0 1. So, the total matrix was equal to 1 plus epsilon 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 1 plus epsilon, and therefore, the eigenvalues are obtained by 1 plus epsilon minus lambda epsilon epsilon 1 plus epsilon minus lambda. This is equal to 0. So, you have 1 plus epsilon minus lambda whole square is equal to epsilon square. So, you can write down lambda minus 1 plus epsilon is equal to plus minus epsilon. So, you will have, if I take it to that side, so you will get lambda is equal to 1 plus epsilon plus minus epsilon. So, you have here two eigenvalues. One is for the upper this 1 plus 2 epsilon and the other is just 1. So, these are the rigorously correct eigenvalues for H, and if you find out the corresponding eigenkets, then that will be 1 1 under the root 2 and 1 by root 2 1 minus 1. We also say that by introducing this perturbation, the degeneracy has got lifted. The degeneracy has got lifted. Now, let me consider another example, a very important example, and that is the example of the Stark effect. Now, we have here let us consider the hydrogen atom problem, and we represent the ground state by U0. The first excited state, this is n is equal to 1, the ground state has an energy equal to E1, which we know as to be minus 13.6 electron volts, it is a minus number, and this the n equal to 2 state is 4-fold degenerate. So, n is equal to 2, then you have L is equal to 1 or L is equal to 0. When L is equal to 1, you have m equal to plus 1 0 minus 1. So, this will have 4-fold degeneracy, 4-fold degeneracy. So, you will have 4 wave functions u1, and that is first let me consider that L is equal to 0. So, R20 Y00, n is equal to 2, L is equal to 1, L is equal to 0, when L is equal to 0, m must be 0. So, Y00 is nothing but under root of 4 pi. So, this is 1 over 4 pi R20 of R. Then U2 will be R21, and when L is 1, this is RNL, RNL, L is 1. So, m can be 0, and this will be under root of 3 by 4 pi y10 we had derived R21 of R cos theta. And then you have another wave function R21 y11, and that is equal to minus under root of 3 by 8 pi r 2 1 of r sin theta, and since this is 1, so this is e to the power of I phi, and u 4 is equal to, this is the Stark effect problem that we will be considering, Stark effect in hydrogen atom, r 2 1 y 1 minus 1. So, m is equal to minus 1. So, sin to the power of L theta, that is sin theta, but this will be plus under root of 3 by 8 pi r 2 1 of r sin theta e to the power of minus I phi. So, these are the 4 wave functions that I have typed out. So, u 1, this is the n equal to 2, n equal to 2. So, we will have L equal to 1. So, if you write down psi n L m, so you will have, this is the first is psi 2 0 0, this is psi 2 1 0, this is psi 2 1 1, and this is psi 2 1 minus 1, and r 2 0 of r and r 1 2 1 of r are known function. These are the radial functions which we had expressed in terms of the confluent hypergeometric functions. So, these are the wave functions that we have chosen for the degenerate state, and of course, for since it is a degenerate fourfold degenerate state, any linear combination of them will also be a wave function. Now, let me put the hydrogen atom in an electric field. Now, hydrogen atom, let us suppose hydrogen atom consists of an electron and a proton. Let the electron be position coordinate is r 1 and the proton position coordinate is, so it has a dipole moment is equal to q, where q is the, and r 2 is the position vector of the proton minus r 1. So, if I write down the relative vector of the electron with respect to this is r 1, this is the relative coordinate that we had introduced while solving the hydrogen atom problem. So, this will be minus q r dot, this is the dipole moment of the hydrogen atom, and in the presence of the electric field, the perturbation is minus p dot the electric field. I am using a script notation, so that we use the notation capital E for the energy. So, this is the electric field. So, let us suppose the electric field is in the z direction. So, E is equal to the magnitude of E in the z direction. So, the z direction will be therefore q E z, this is the perturbation, and this z in spherical polar coordinates is just r cos theta. So, this is my perturbation. In the presence of an electric field, this is the perturbation. In the presence of magnetic field, there will be another expression for H prime. We will consider relativistic correction and spin orbit correction. In each case, the Hamiltonian will be different. For the Stark effect problem, the H prime is given by this. So, now I have a fourfold degenerate state u 1, u 2, u 3 and u 4. So, the recipe is we find out first all the matrix elements H prime I j, that is H prime 1 1, H prime 1 2, H prime 2 1, H prime 1 3, H prime 1 4, H prime 4 4. So, there will be just 16 such elements that we have to calculate. So, we first calculate H prime I j, where I, H prime j, and I goes from 1 to 4 and j goes from 1 to 4. So, you will have a total of 16 matrix elements, 16 matrix elements. and let me, it is a brute force calculation. So, let me first calculate this matrix element. So, my U3 is say minus under root of 3 by 8 pi, let me write it down clearly, R21 of r sin theta e to the power of I phi, and U1 is, let us suppose, 1 over root 4 pi R 20 of r. This is psi 2 NL1 NLM, and this is psi 200, and my H prime is equal to Q E R cos theta. So, let me calculate, say, H prime 3 1 or 1 3, does not matter. So, this is bra 1 H prime get 3, that is, this is a shorthand form for writing that U1 star H prime U3 d tau. So, U1 star is, let me write it down. So, H prime is Q E R cos theta. So, let me write down what is U1. So, 1 over root 4 pi, U3 will be minus under root of 3 by 8 pi. You have to patiently write it, and then first the R integral. So, R integral will be R20 R21 times R square times R here, that is R, and then the volume element will consider R square dr from 0 to infinity. The theta integral will be sin theta, and the volume element consists of R square dr sin theta d theta d phi. So, this is d tau. So, R square dr I have taken. So, sin theta d theta multiplied by sin theta. So, sin square theta cos theta d theta, and then the phi integral will be, that is the most important, will be e to the power of I phi multiplied by e to the power of I phi U1 e to the power of I phi d phi from 0 to 2 pi. This limit will be from 0 to pi. Now, because of this will be 0. So, we will have H prime 1 3 will come out to be 0. Similarly, if you calculate H prime 2 3, that will be 0, H prime 1 4, that will be 0. The only two non-vanishing matrix element will be H prime 1 2 is equal to H prime 2 1 is equal to a constant quantity which I denote by G. So, you see, let me tell you once again that, for example, in this I have calculated H prime 2 3. So, H prime 2 3 is U2 star H prime U3 d tau, and what is d tau? This d tau is R square dr sin theta d theta d phi, and this is actually a triple integral as I have shown here. So, the R, so U2 will be U2 star, the R and theta part is this R theta phi, this is the perturbation, this is U3 multiplied by r square dr sin theta d phi. Because of this term e to the power of I phi d phi, this integral from 0 to 2 pi is just 1. Oh, I am sorry, this is just 0, I am just sorry, this is 0. So, the total integral comes out to be 0. Similarly, however, the only non-vanishing integral is h prime 1 2. So, you calculate, this is multiplication of, so so both of them is y 0 0 and this is also y 0 0. So, y 0 0 will be, the angular part will be y 0 0. So, that is 1 over root 4 pi, and this integral will be just you have to calculate this. This integral will be 2 pi, and there is a r cos theta term which is because of the perturbation, and it will come out like this. So, that comes out to be G. So, only non-vanishing, one has to spend some time in brute force calculating these. The only two non-vanishing matrix elements will be h prime 2 1 2 is equal to minus G, where G is equal to 3 q E. E is the strength of the electric field, and A 0 is the Bohr radius. A 0 is h cross square by mu A square. So, once again I have a four-fold degenerate state, and these are the 4 eigenfunctions u1, u2, u3, u4, and r2 0 and r2 1 are given by. So, we could have chosen any linear combination of them also. Now, we have this perturbation h prime which is equal to h prime which is equal to q e r cos theta. So, we had this, and then we calculated laboriously all the matrix elements, and we found that all the matrix elements are 0 excepting for h prime 1 2 and h prime 2 1. So, therefore, if I write this down, so you may remember that we have to we have to write down this equation. We said that if it is a three-fold degenerate state, you will have a set of 3 equations. If you have two-fold degeneracy, you will have a set of 2 equations. If you have a set of three-fold degenerate state, you will have a set of 3 equations. If you have a four-fold degenerate state, you will have a set of 4 equations. Now, this term is 0, 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 this term is 0. So, only, so in general we have to, if all of them are non-zero, this is the determinant that we have to solve. But let me do it, let me take the values of the different matrix elements. So, we will have h prime 1 2 and h prime 2 1, h prime 1 2 is equal to h prime 2 1 is equal to minus g. So, please see this. My objective is to calculate the perturbation. So, please see these 4 equations simplify to C 1 minus sign W 2 1, this is the first term, minus C 2 G plus 0 plus 0. So, this is equal to 0. The second term is C 1 minus G minus C 2 W 2 1, this is equal to 0. then C3 multiplied by minus W21, this is equal to 0, and similarly C4 is also like that. Actually, we will have a determinant like this, 4 by 4 determinant, but it simplifies because these are two are coupled and these two are not coupled, but we can say these two equations tell us that either C3 is 0 or W21 is 0. So, the first two equations tells us that W21 square is equal to G square. So, the perturbation is W21 is equal to plus minus G. The second tells us that if W21 is anything else other than 0, then C3 must be 0, C4 must be 0. But if I choose W21 equal to 0, then C3 and C4 can be arbitrary. Now, first let me write down the first two equations. So, if I take the minus sign out, so we get C1 W21 plus C2 G is equal to 0, C1 G plus C2 W21 is equal to 0. So, the determinant must be 0. So, therefore, W21 whole square will be equal to G square, and then W21 is equal to plus minus G. For plus G, so for W21 equal to plus G, you will have C2 will be equal to minus C1, and my wave function will be U1 minus U2 by root 2. And for W21 equal to minus G, C1 is equal to C2. I think I am right. This is U1 plus U2 is divided by root 2. Root 2 factor is just for normalization. Now, the other two equations, these two equations tells us W21 is 0. If W21 is 0, then C1 must be 0, C2 must be 0. So, if W21 is plus G, then C3 comma C4 must be 0. C3 comma C4 must be 0, and the 4 roots are therefore W21 is equal to 0, then C3 and C4 can be arbitrary. So, therefore, we obtain the following that this is the n equal to 2 state, this is plus G and this is minus G. So, the n equal to 2 state, of course, I am neglecting spin, splits into 3 states. The first, this U3 and U4, the first order perturbation is 0, and so for this the degeneracy is not lifted. But for the other there is these two states which split, the wave functions are u1 plus u2 by root 2 and u1 minus u2 by root 2. And the question arises, as we had mentioned, that what is u1 and what are u1 and u2? We had mentioned that u1 is r20 y00, r21 y10. So, u1 as you recall was r20 of r, y00 of theta phi, and y00 as you remember is just 1 over root 4 pi. This is the spherical harmony, and u2 is equal to r21 of r and y10, and what is y10? That is just under root of 3 by 4 pi cos theta. So, they both correspond to m equal to 0 states. So, this splitting of the n equal to 2 state is known as the Stark splitting. Stark splitting. Now, I leave it as an exercise for you that instead of u1, u2, u3, u4, you start with these wave functions phi 1, phi 2, phi 3, phi 4, where phi 1 is equal to u1 plus u2 by root 2, phi 2 is equal to u1 minus u2 by root 2, phi 3 is equal to u3, and phi 4 is equal to u4. If we start, because these are also well behaved eigenfunctions, orthonormal eigenfunctions, sorry, this is square root of 2. So, orthonormal eigenfunctions corresponding to the n equal to 2 state. These are the 4 linearly independent orthonormal set of functions. I leave it as an exercise for you to show that h prime I j is equal to 0 if I is not equal to j. That is, if we choose phi 1, phi 2, phi 3 and phi 4 as the base vectors, then any matrix element like phi 1 h prime phi 3 or say integral phi 2 star h prime phi 4, any one, that is 0. Only the diagonal terms survive, and you will find that the two terms that will survive will be say phi 1 star h prime phi 1 d tau. This will be come out to be minus g, and phi 2 star h prime phi 2 d tau, this will be plus g, phi 3 star h prime phi 3 d tau, this will be 0, and phi 4 star h prime phi 4 d tau is equal to. So, we have an all other matrix element. So, all other matrix element are 0. Of course, I have h prime is equal to q e z, that is equal to q e r cos theta. So, you will have, so only the diagonal terms will be there, and my secular matrix will be minus g minus w1 0 0 0, this will be 0, then 0 plus g minus w1 0 0, and then 0 0 minus w1 0 0, 0, 0 minus W1. And the eigenvalues, the perturbations therefore will be W1 will be minus G, plus G, 0 and 0. So, we then, if we start out with a representation in which H prime is diagonal, if we start out with with those set of unit vectors in which H prime is diagonal, then it is fortuitous and the diagonal elements will represent the perturbation. So, in this particular case, the diagonal those are, this is phi 1 that we had chosen and this is phi 2. Okay. We then consider another simple problem, and that is that if hydrogen atom, we neglect spin. For hydrogen atom we cannot neglect spin, but let us suppose we neglect spin and we assume a magnetic field in the z direction. Now, if I apply a magnetic field in the z direction, then the perturbation will be the, you see, for the hydrogen atom you have here a proton and an electron is in the Bohr's model. You can assume that it is rotating in a circular orbit. So, if I am sitting on the electron, the proton is rotating at this thing. So, because of the orbital motion, there is a magnetic moment, there is a magnetic field, and there is a magnetic moment which interacts with the magnetic field, and the perturbation is equal to minus the magnetic moment times the magnetic moment due to the orbital motion of the electron multiplied by B, and this comes out to be plus QB by 2 m. M is the mass of the electron multiplied by Lz. I am assuming that the B field is in the z direction. So, this we usually write it as mu B B by H cross Lz. And what is mu B? Mu B is equal to Q H cross by 2 m, is known as the Bohr magneton, and the value is 9.274 into 10 to the power of minus 24 joules per Tesla. So, I consider the orbital motion of the electron. I neglect that the electron itself has a magnetic moment. Because of the orbital motion of the electron, it has it sees a magnetic moment because of the orbital motion, and therefore, there is an interaction energy with the when a magnetic field is applied, and that interaction energy is given by this. So, mu B is a constant, B is a constant, and of course, H cross is a constant. Now, I have a magnetic field, a static magnetic field which is applied in the z direction. Now, in the hydrogen atom problem, you have H naught psi NLM is equal to E sub n psi NLM, and therefore, psi NLM, as we all know, is RNL YLM, and you recall that YLM are known as the spherical harmonics. the spherical harmonics are simultaneous eigenfunctions of L square, this is equal to L into L plus 1 H cross square y L m, and Lz y L m, the spherical harmonics are also simultaneous eigenfunctions of Lz m h cross y L m. So, the hydrogen atom wave functions are eigenfunctions of the operator Lz. So, when Lz or H prime operates on this, so please see that Lz y L m is equal to m h cross y L m. So, H prime, what is H prime? As I said that this is equal to mu b b by H cross, because just of the orbital motion. Lz is the z component of the orbital angular momentum. So, H prime psi n L m is equal to Lz psi n L m. So, therefore, this will be mu b b H cross times m H cross psi n L m. And if I now multiply by psi star, same value of n, but different value of L prime and m prime, and I integrate H prime psi n L m d tau, which is a 3-dimensional integral. So, this will be H cross H cross. So, mu b b times m, and this is psi star n L m. So, n and n are equal, because two different values of n will correspond to different energy. This is n is equal to 1, n is equal to 2, and n is equal to 3, and so on. So, this will be delta L L prime delta M M prime. So, we already, because the magnetic field is assumed to be in the z direction, we already have a representation in which H prime is diagonal, because any off diagonal elements are 0. So, therefore, this will represent the perturbation, and this is known as the normal Zeeman effect, and any value of L will make it split into different values of m. Unfortunately, this theory is not applicable to hydrogen atom, because we have to take into account the effect of spin and the spin orbit interaction and other things. However, if I have a singlet state like in cadmium, then S is equal to 0. So, this is the singlet D2 state, this is the singlet D2 state. So, L is 2, singlet means S is equal to 0. So, we neglect, there is the spin is 0. And so, therefore, because L is 2, so m will be minus 2, minus 1, 0, minus 2, minus 1, 0, plus 1 and plus 2. This is the normal Zeeman splitting, and this if I assume a transition to singlet P1, here S is again 0 and L is 1. So, m can take values minus 1, plus 1, minus 1, 0 and plus 1. And the selection rules are, that is, transition takes place when change in ml is 0 or plus minus 1. And as you can see from the figure, the splitting is the same here as well as here, and therefore, it results in a Lorentz triplet This is what is known as normal Lorentz triplet. There are 3 lines. So, therefore, if I am able to neglect the spin term, then the interaction occurs only with the orbital motion. If the spin term is 0, then my Hamiltonian is proportional to Lz, and fortunately we have a representation which is an eigenfunction of Lz, and so therefore, we have a representation in which H prime is diagonal, and so therefore, diagonal elements represent the perturbation, and in this case the diagonal elements are, I wrote down. So, this is M H cross, the diagonal elements are Lz, therefore, M mu b times b. So, it is proportional to M, and therefore, this splits, the splitting is proportional to. So, this corresponds to M equal to plus 2, and this corresponds to M is equal to minus 2 and this leads to what is a normal Zeeman triplet. If you ask me the question that what would have happened if I had applied a magnetic field in the x direction? Of course, there is nothing sacred about the z direction. Then what would have happened is, these are eigenkets of Lz. If you assume that this to be Lx, then YLM are not eigenkets of Lx. You would have obtained non-diagonal elements, but the final result would have come out the same. The final splitting would have come out the same, and the eigenkets that you would have obtained would have been eigenfunctions of the operator Lx. So, that YLM are the eigenkets of L square and Lz, but if you take linear combinations of them, then you can form eigenkets of L square and Lx or of L square and Ly. And so, therefore, if I assume the magnetic field to be in the x direction, then the calculations would of course become very cumbersome. You would have had to calculate matrix elements, but the final result, this actual splitting, would have come out to be the same. So, I have told you 2 very important examples. One is the stark splitting of the n equal to 2 state of the hydrogen atom, and the Zeeman splitting corresponding to the Zeeman splitting when we neglect the spin of the electron. Now, we will just introduce what is known as the relativistic correction, and then we will conclude today's lecture, and then we will solve for the fine structure of the hydrogen atom in my next lecture. So, as you know, we will discuss the relativity corrections, due to relativistic effects. You have the Einstein's equations, E square is equal to C square P square plus M square C4, where M is the rest mass of the electron. In the presence of a potential energy, you will have E minus V of r whole square is equal to C square P square plus M square C4. So, I write the corresponding relativistic Schrodinger equation. I represent Px, Py, Pz by the Px by minus IH cross delta by delta x and so on. So, this will become minus H cross square C square del square plus M square C4 psi is equal to E minus V of r whole square times psi. I write E as equal to E prime plus MC square. So, my right hand side becomes E prime minus V of r, I put that within brackets, plus MC square psi. Sorry. So, I square this and obtain the following expression. So, you will get for the left hand side minus h cross square c square del square plus m square c 4 psi is equal to E prime minus V of r whole square times psi plus m square c 4 psi plus 2 m c square E prime minus V of r psi. I just squared this expression. This term cancels out with this term, and I obtain this particular equation. I divide the whole equation by 2 m c square. So, I will obtain h cross square by 2 m del square psi. I divide the whole equation by 2 m c square, and then I bring it to this side. So, minus E prime minus V of r whole square by 2 m c square psi minus E prime minus V of r psi is equal to 0. So, I rewrite this, take the E prime on the other side. So, I can write this as H naught plus H prime psi is equal to E prime psi, where H naught is minus H cross square by 2 m del square minus minus plus, that is V, and H prime is this whole term, that is E prime minus V by 2 m c square whole square with a minus sign. Of this I know the solution. So, I will take this as an unperturbed Hamiltonian, and in my next lecture I will consider this as the perturbation and calculate the effect of this correction term. This correction term is to take care of effects of relativity, and this correction are known as the relativistic correction, and we will discuss this in the next lecture. Thank you.